Today's topic, the derivative by definition. So let's talk a little bit about what the derivative is. Well, let's first kind of talk about our goal. Our goal is to be able to figure out the derivative of a function at a specific x. Derivative is the rate of change of your function. So by the end of this, we should be able to figure out basically the slope, not even basically, exactly the slope of our function at a specific point. So why is that tough to do? Well, first of all, when we think of slope, we think of the slope formula, or we should think of the slope formula, which is y minus y over x minus x, right? So if I want to figure out the slope, that means that I need 2 points up to this until you get to the calculus. Every time you want to figure out slope, you have to be given 2 points, and then you use those 2 points to figure out what the slope is by doing y minus y. So here's a function. So here's our function is the x squared graph. If I want to figure out what happens at this dot right here, I want to figure out the slope of the tangent line at negative 0.5. Well, this is tough to do because so first of all, here's what the tangent line looks like. That red line there is the tangent line. And the problem with this is I'm only given 1 point. Now our computer has calculated this for us using 2 points because it can figure out this actual line. It actually did the difference formula for us, difference quotient, the derivative by definition. That's what this all is, and I'll get more into that later. I just want to talk about the idea. So the idea is I want to figure out the slope at this one dot. So this is what we call the tangent line. It's this line that comes in. It only hits the curve at one place, and it kind of like teeter-totters on that one spot. So it only hits the curve at one place. Well, if we only have 1 point, now we could try to measure where these other points are, but we don't know where those other points are exactly. The only point we know for sure is this point right here. So this is what our boy Leibniz and our boy Newton came up with. This is their method of figuring out the slopes. They said, okay, what I'm going to do is I'm going to take a second point. That's this point right here. I'm going to take that second point, and that second point is also on the curve. It's somewhere on the curve. I don't know where it is, but it's somewhere else on the curve. Now, what's nice about having 2 points, look, we know where this is because it's on the curve. We can plug in that x value. We can plug in this x value, whatever it is, and we get a y value, so we have 2 coordinate pairs. So we can figure out here the slope. The problem is this is the slope between these 2 points and not the slope at this spot right here. We call that the average rate of change. This is the slope formula. I know it looks a little nasty, but remember f of x is just y. So this is basically y minus y over x minus x. So what Newton and Leibniz decided to do was they said, well, let's take the limit of the slope formula. I know this doesn't feel like the slope formula, but I'll talk a little bit about why it is. As h approaches 0. In other words, as this distance away from the point that we want to figure out the tangent line gets smaller and smaller and smaller. So as I move this point closer to this point, its x value closer to that, as h gets smaller, look what's happening to this is called the secant line that hits 2 points. We call that the secant line. The one that hits only 1 point is called the tangent line. But look what's happening to the slope of the secant line as we get closer and closer and closer and closer to that point. So the secant line starts to become the tangent line. So algebraically, what we can do is we can figure out the slopes, slopes, as this gets infinitely close to 0. Now, you can't do this graphically because you're always going to have some sort of a gap, but we can do it algebraically because of the power of the limit. This is what the limit allowed us to do. It allowed us to deal in infinitesimals, and it allowed us to deal with infinity. So the limit is, remember, where does the graph intend to go? So as I look at the slopes of this blue line, okay, the slopes. If I had a table of all those, I could start to predict as I got closer and closer and closer to the point where we want to figure out the slope. I could use that to predict what's going to happen to my slopes. So that's what the derivative by definition basically is. It's the slope formula. So this is f of something minus f of something else. So that's y minus y over, and then this is your x values. So what I'm doing is I'm picking an x value, and then I'm picking another x value that is getting closer and closer and closer to 0. So when I subtract the difference between the two, eventually those two things should become 0. So hopefully that helped explain a little bit, maybe not. I'll try to keep talking more as we go through the notes on what this thing called the derivative is. It's the slope at a single point. Now we can't do the slope formula with only one x and one y, so we go a little bit away from x with this other point, and then we try to get that point closer and closer and closer to 0, which we could do graphically, but it wouldn't get us a very good estimate, but we can do it algebraically and get dead on, get exactly what we want. So let's take a look. Grab your unit circle. You can put this on there. You don't have to memorize it, but you're going to write it so much that hopefully it'll start to stick in your head. But this is saying, okay, so let's look at what this is. This little plus h is some distance away from h. So if I were sketching a little graph of this, and I've got some function, okay, I don't know what my function is going to look like, but this is what I'm going to call x. And we're going to move some distance down the line. It could be backwards as well. And we're going to call that distance here called h. So that's going to give me a new coordinate called x plus this distance of h. Now my function, I don't know what, I'm going to probably regret drawing it the way I'm going to draw it. So let me try to think for a second. I guess I'll try something like this. I want the tangent line right here. The problem is I don't have a second point to do y minus y with. So what we're going to do instead is we're going to go a little bit farther away. This h is going to be some number, and it's going to track up here, and I'm going to take this slope, okay, the slope of that line, and then I'm going to make h a little bit smaller, and I'm going to get here, like I did with the computer, which did a much nicer job of showing this. I'm going to keep making h go smaller and smaller and smaller and smaller until I get h to be 0, and that's the limit. Now look at what my function would be. So if I were doing my y values, this point is called f of x plus h. That's my y value. So if I go to this and I track up here, that's f of x plus h, minus this y value here, which would be f of x, over this x value, x plus h minus x. So now, where did the x's go? That's why there is no x in the bottom, because when you do the difference quotient is what this is called, x minus x is always going to cancel out, and we just basically have h on the bottom. I mean, think about what the slope formula is. Another way to write the slope formula is change in y over change in x. Well, what do we want this distance, this h, this change in x to eventually be? We want it to eventually become 0. So anyway, there's sort of a long-winded explanation on where the formula comes from. So we're going to do this algebraically. The first part is me being picky math guy. So these are derivatives by definition, which means you have to be very formal in the way that you write them up. If this is just, evaluating a limit, it's a different story. These are derivatives by definition. So it's almost like our trig proofs, where you have to be really precise in the way that you write things. So we're trying to find the derivative. This little tick mark here, that's described as f prime, and it means the derivative of f. So we're trying to find the derivative of f of x. That would be called f prime of x equals the limit as h approaches 0. So all I'm doing right now is plugging and chugging into this formula. So remember, if I said to you, what's f of 7, and this was my function, what would you plug in for x? 7, right? Well, now we're evaluating f of x plus h. That means all the x's are going to get replaced with x plus h. So f of x plus h becomes x plus h squared minus 5 times x plus h plus 2. So I replaced all the x's with x plus h. Then I have to subtract the function. Well, when you subtract the function, what's going to happen to each one of these signs? If you're subtracting x squared, you'd get minus x squared. If you're subtracting negative 5x, you'd get positive 5x. If you're subtracting positive 2, you would get subtract 2. All over h. Now we're going to start to do some algebra from here. We're just going to try to start to clean things up. You have to write the limit every single time until you can get to a spot where you can direct substitute the 0 in for h. Now, we can't do that right now because we would get a 0 on the bottom. So we got some work to do. That means the limit is still alive, and you have to write it every single time. X plus h squared. Hopefully you can do that in your head. If you can't, go over to the margin. X plus h squared really means x plus h times x plus h. Now I'm going to start to distribute that. That's x squared plus xh plus hx plus h squared. X squared. Remember, xh and hx, just flip them around because multiplication is commutative, and we'd get this. That's the only time I'm going to show that the long way, because I've done so many of these, and you're going to get to the point where you're going to do so many too, especially those who are going on to AP. This is what I call a 1-2-1. 1, 2, 1 are the coefficients, and it's x squared, xh, and h squared. That's what we call a 1-2-1. So x plus h squared expands into x squared plus 2xh plus h squared. Then I'm going to distribute the negative 5, so that's minus 5x minus 5h. And the rest I'm just going to write now because there's nothing to clean up, all over h. This is formal. This is a proof by definition. So you have to write out every single little detail. So this equals the limit. I haven't been able to plug in 0 yet for h, so I have to keep writing it. Now, if you did this correctly, lots of good mathemagic should happen at this spot. Everything without an h should cancel out. So as I look through x squared, yep, I've got a minus x squared. That has an h, that has an h. Minus 5x, yep, down the line there's a plus 5x. That has an h, plus 2, minus 2. Everything, if you've done this step correctly, this is your first sort of milestone or checkpoint or save place if you're playing video games. This is your first save. You know you did this right if everything without an h cancels. So that would be 2xh plus h squared minus 5h all over h. Now notice, what do you have? Everything has a h, which means we can now we can divide everything by an h. So I'm going to cancel this 1h. I'm going to cancel this 1h. Now it says h squared, but I'm going to kill the squared, so that h is still alive. This 1h, they all get divided by that 1h. Now, if you wanted to factor out an h, that's why it's legal. I'm not going to get into that algebra part right now. So now I'm going to write again. This is now the limit as h approaches 0 of, okay, what are we left with? 2x plus h minus 5. The h on the bottom is now gone, which means we can finally direct substitute 0 in for h. So 2x plus 0 minus 5 ends up being 2x minus 5. Now, those of you who have taken physics, you might already recognize that there's this derivative shortcut thing, and I promise we'll get there. It's called the power rule. I promise we'll get there. But right now we're doing derivatives by definition, which means you have to show all these little steps. Okay, let's see how you do. I'm going to encourage you to pause and try to do example 2 on your own. Okay, let's see how you did. So I'm going to start off with my f prime of x. Hopefully you wrote small. I'm noticing that I got to write pretty small to fit this in here. I'm taking the limit as h approaches 0, and I'm going to go through. I'm going to replace x with x plus h. So this becomes 3 times the quantity x plus h squared plus 2 times the quantity x plus h minus 4. Now that's just the first part. Then we need to subtract the function. So when I subtract the function, all the signs are going to switch around. Minus 3x squared minus 2x plus 4 all over h. Now look at right away, before I even start to look at how to clean up, I write that limit so I don't forget it for the next step. Okay, so we talked up here, x plus h quantities squared is what we call a 1-2-1. Well, if you've got a 3 out in front of this, what's going to happen to all these coefficients? They're going to get multiplied by 3. So I don't call this a 1-2-1, I call this a 3-6-3, because the 1-2-1 needs to get multiplied by 3. So that's going to be 3x squareds plus 6xh's plus 3h squareds. Then I'm going to distribute the 2. So that's 2x plus 2h. And then the rest, there isn't anything I can do right now. All right, we're at our first checkpoint. Notice I'm not even thinking, I'm talking, and I'm writing this stuff down that I know is going to carry over. Now I'm going to start thinking. At this point, I can start to kill stuff. So I should be able to cancel what? Everything without an h. So 3x squared, yep, and a minus 3x squared. 2x and a minus 2x, yep, and a minus 4 and a plus 4. Everything else has an h. 6xh plus 3h squared plus 2h over h equals. I haven't been able to plug in yet, so I've got to write the limit again. So it's kind of tempting to be able to, at this stage, to cancel the non-h's and then cancel the h at the same time. I'm going to be picky about that. I've got to make sure that you know how things are reducing. So you may not cancel out and cancel the h at the same time. So if you do, I'm sorry, I'm going to mark it. You're going to lose some points there, because I need to see this as a proof, and I need to see that you understand how things cancel, not just that they magically do. So at this point, everything has an h, so I can kill 1 from each piece. That leaves me with a 6x plus 3h plus 2. Finally, I killed the h on the bottom, which means I can take the 0. Oh my gosh, I'm blowing up over there. I can now take the 0 and plug it in, and I get 6x plus 2. So that equation, how does that fit with what we talked about before? That represents all of the slopes. Okay, so if I wanted to figure out what is the slope of the tangent line at 7, I would take 7 and plug it into this. This is the equation for all of those tangent line slopes that I talked about earlier. Remember, the derivative is the slope of the tangent line. This is the equation for all of the slopes of the tangent lines. Those who take AP will get way more into it. That's a whole semester of conversation right there. All right, so from here on out, I think hopefully you've got the idea. Everybody should be able to get 1 point. The first point is this line right here. That means plugging in x plus h in for x and then subtracting the function all over h with the limit. Cleaning it up from there, that depends on your algebra skills. So the next two, I'm not going to have a you try. I'm going to save that for the homework. But the next two, I'm going to show you the trick on how to clean these bad boys up. All right, let's take a look at... I'm gonna encourage you to pause here and see if you can do the first step. That's just writing out the difference quotient, or the derivative by definition, I should say. All right, let's see how you did. So I'm always going to start off f prime of x equals the limit as h approaches 0. I'm going to take out x. I'm going to replace it with x plus h. So in this case, that's going to look like 3 times the quantity x plus h minus 2 underneath the square root. And then I'm going to subtract the function, which was 3x minus 2, all over h. There's 1 point right there. The next 2 points come from, the next point is cleaning up the algebra, and then the last point is actually getting the correct answer. Okay, so I want to choose a nice blue here. I want to figure out a way. Well, you can direct substitute if you want. You'll see that you'll get 0 over 0. So there's a hole here. There is a hole. We've got to figure out where that hole is. As you can tell, we've got some roots on the top. So that's the biggest problem we've got to take care of. We've got to free these things from their roots. Unfortunately, we can't just square the top and square the bottom. That's not mathematically legal. So what is the way that we can square something without actually squaring it? We've done this a number of times now. We're going to multiply by the conjugate. So the conjugate is the exact same as what it was before, except for the sign in the middle. So this stayed the same, that stayed the same, and the sign in the middle changes. Now, if you multiply the top of a fraction by something, you must multiply the denominator by the same thing. Otherwise, you are changing the value of your fraction. Okay, so can we plug and chug yet? We cannot. That's why we have to write the limit again. Now let's watch what happens, and I've done this a number of times, so hopefully you remember it. But let's watch what happens when we try to distribute distribute conjugates together. What would be a good? I'll go with, I guess, a boring gray, because I want to use purple and orange. I could use orange. How about orange? That's too close to pink. Whatever. We'll use gray. Okay, so when I distribute this times this, so root 3 times the quantity x plus h minus 2 times a root 3 times, I'm going to get 3 times the quantity x plus h minus 2. And then the next two distributions are where the math and magic happens. I take this times this. Whatever that is, it's going to be some disaster of a root. Root this times root that, but it's positive. My next distribution is going to be those same two nasty roots, except it's negative. So when I add those two things together, what's going to happen to those roots? They gone. So this distribution and this distribution are going to cancel each other out. So I don't even have to write those down. The power of the conjugate. Now I'm going to take this, I'm going to distribute to this. What's going to happen to those roots again, because they're the same thing? They're going to cancel, except this was a negative and this was a positive. So a negative times a positive is still negative. So it's got to switch these signs. So that's going to become a minus 3x and a positive 2. If you're not sure, pause and think through that. Your algebra skills are good enough. You could figure that out on your own. Okay, now from here, I'm going to still need to distribute the bottom. So we traded a nice, neat numerator for a disaster of a denominator. But that's okay. That's going to work itself out later. So this is still underneath a root. This is still underneath a root. Okay, let's see now. I'm going to be a little lazy, and I'll let you be that same level of lazy. You don't have to rewrite everything just to distribute this. I probably should have distributed at the same time, but I didn't want to get too confusing. So I'm going to get a little lazy here, and I'm going to write 3x plus 3h above that. You don't have to show your work there. That's fine if you want to combine those two steps. I'm okay with that. So let's see. What should happen here? Non-h stuff should cancel. So I've got a 3x squared, a 3x, and a minus 3x, a minus 2 and a plus 2. So that leaves me with the limit as h approaches 0 of 3h over h times the quantity, and I know it's a pain, but you got to rewrite this. We can't shortcut that part. Minus 2 plus 3x minus 2. Oh boy. What's good about this? What do you notice we have on the top? H. What do you notice we have on the bottom? H. I can now cancel an H for an H. That H in the denominator was the H that was causing us to be unable to distribute this 0 in. So now that I've killed this H here, I can now put this 0 in for this H. And let's see what we're left with. So I would have just the 3 on the top over. Okay, so I put 0 in there. This would become 3x. So this would become 3x. I didn't extend my root long enough. Sorry, I want to fix that. That goes over the whole thing. So when I put the 0 in here, I would get 3x minus 2. This root is also 3x minus 2. So what's root 3x minus 2 plus root 3x minus 2? It is 2 root 3x minus 2. Man, I don't know. Maybe next year I'll print this with some more space. It's pretty tight. I like having it all on one side, though. Yeah, that's okay. All right, let's take a look at the other scenario. So here's the best way. This is the one we like the most. This is the derivative by definition of a polynomial. Oh man, plug and chug makes you feel real smart. Pretty straightforward. Things get a little bit more complicated when we talk about roots. We've got to create the conjugate so that when we distribute, those roots in the numerator cancel out. The roots in the bottom will not, but when you clean up at the end, those roots will be the same terms, and so you can combine those two together. All right, let's take a look at what happens when we have a rational function. So I'm going to encourage you to pause here and try to write up what f prime looks like according to the definition. All right, let's see how you did. So this would be the limit as h approaches 0 of f of x plus h, which would be 2 over 3 times the quantity x plus h minus 4, minus the function itself, 2 over 3x minus 4 over h. I wish I wouldn't have put that there. That does not belong. So I don't know why I made that division so far. So we've got a fraction. Subtract another fraction. If you want to put fractions together, you must have a what? Common denominator. So a guaranteed way to make two denominators the same is to multiply them by each other. So 3x minus 4. I'm going to distribute this now, kind of like up here where I had to distribute later. I'm going to distribute that now. So this is going to be 3x plus 3h minus 4. So we get now this one big limit, the limit as h approaches 0 of, so first of all, I have a common denom. So my common denom is 3x plus 3h minus 4 times 3x minus 4. Now remember, this is all over h, so I'm going to put mine in there right now so I don't forget about it. So I've forced myself to have a common denominator. I know I only wrote it on the top, but I'm multiplying the top and the bottom by this. Now up here, I've got to distribute. So 2 times 3x becomes 6x minus 8. Now I'm going to distribute this 2, but I'm going to distribute that as a negative 2. So I would get negative 6x. I would get negative 6h, and I would get positive 8. We ran out of room. I haven't been able to plug in 0 for h yet. Let's try to clean this up. So what should happen here, we've done this a couple times now, everything without an h should go. 6x minus 6x, negative 8 plus 8, they gone. So now my numerator is negative 6 over h over 3x plus 3h, dang it, minus 4 times 3x minus 4. I'm definitely reprinting this next year. Sorry. All over h. So, numerator looks pretty nice. Denominator is kind of a mess, but they look similar to each other, so I'm not too afraid of that. It's this h on the bottom that's still causing me to not be able to plug in 0 for h. But this is, at the end of the day, is a what? On top is a what? Fraction. When you try to do a fraction divided by something, nobody can do that. What do we have to do instead? We turn the thing in the denominator to a fraction and flip and multiply. Flip and multiply. So what should happen now, my h's actually do cancel out. So I'm left with the limit as h approaches 0 of negative 6 over 3x plus 3h minus 4 times 3x minus 4. Finally, I can put this 0 in for h because it's not going to cause a 0 in the denominator. So I'm left with negative 6 divided by, so when I put 0 in here, this term would be gone. So I'd have 3x minus 4 times 3x minus 4, which would be 3x minus 4 squared. Okay, so like I said, I do not have examples for U-tries on these last two. We did a U-try here to get the basic plugging in idea, and then I went through and did the heavy lifting for these two. I really encourage you on the homework set to give these ones a try. I mean, it's only 8 problems a piece, but the only way you're going to figure this stuff out is by practicing. So good luck.